So this is a gentle introduction to BERT-type language models. In this demonstration, we will see how BERT models look like, and also use pre-trained BERT models to train simple classifiers. And we will test this classifier on a movie sentiment classification dataset. So as usual, we will start with a series of setup instructions. Some excellent implementations of several language models, including BERT, has been made available via the Transformers library, publicly released by Hugging Face. So let's start with that. We'll also import some basic NumPy and Pandas type packages. We won't be doing any actual deep network classification, so we'll just train a simple logistic regression model at the very end. So we'll import that from sklearn. And while that gets imported, what we'll really be doing is examining a model called Distilbert. So Distilbert is a lightweight BERT model. It has been useful in a bunch of different applications. The high-level idea is to train a sort of surrogate BERT model using a technique called knowledge distillation. This won't get into the details of what that is, but this has the benefit of reducing the number of parameters compared to the original BERT model by approximately 40%, while almost reaching the same accuracy. So let's start with that. Some things to keep in mind here. So we'll download the Distilbert model, and every language model of this kind also has a corresponding tokenizer. So recall that the input is a bunch of text. So text has to be tokenized, and care has to be taken to make sure that the tokenizer that you use to encode the input text is the same as the tokenizer that was used to train whatever language model that you want to use. Okay, so let's do that. That's the Distilbert model. Some features to note here. So one is that it's massive. It's 256 megabytes for just the language model itself. So it's actually maybe useful to see how it looks like. So let's just examine its contents. As you can see here, it's the fairly standard transformer kind of model. So there are series of transformer blocks. Each transformer block is basically a multi-headed self-attention mechanism followed by a shallow MLP. Right? So that's really a transformer block. The Distilbert model has 0, 1, 2, 3, 4, 5. So 6 transformer blocks stacked sequentially. Right? So that's what it does. So 6 blocks. Let's see how many parameters it is. So as you can see, it's a lot of parameters. 66 million parameters. Right? Like it's a heavy amount of lifting right there. So a single forward pass to this model, you can expect to take some more time. So this is in fact one of the smaller language models, and BERT itself is about double the size. Okay. So this is par for the course. So let's see how this does. So to examine the working of this model, we'll also download a data set. So we'll try to do classification, sentiment classification, and the test data set will be a data set called SST2, the Stanford Sentiment Tree Bank. So a data set of movie reviews. And for our purposes, let's just keep the first 2,000 movies. Let's see how they look like. So the training data that we'll have is going to be a sequence of 2,000 such reviews. Each review has basically a bunch of words, text, and a label. A label will be 1 if it's a positive review, So let's say it's a funny, happy, stirring movie, so it's a positive review. On the other hand, or if it's a visually stunning rumination on love, it's a positive review. However, if it's something like too bland and fustily tasteful, that's negative review, so it's 0. Or allegedly inspiring, etc. Right? So that's obviously sarcastic, so it's negative review. Okay, so this is the data set that we'll use. Our goal will be to try and predict sentiments of unseen reviews. Okay, so this is just 2000. It's a very small data set. So you can imagine that this kind of data is not enough to train an entire network, right? Like a real deep network. This is just too small, too few number of samples. But as we'll see, using sort of pre-trained models will dramatically make our life easier. So let's see how that is. In this particular notebook, we won't be fine-tuning the BERT weights or the Distilbert weights. We'll keep them frozen. So in the end, we'll only have to train a simple or shallow classifier. Okay. Also, let's see how balanced this is. So this is 2000 reviews. So if you see approximately 1000 are positive and 950 are, so 1040 are positive and 960 are negative. So pretty well balanced. That's good. Okay. So let's now see how to tokenize our inputs. So we'll have to first take in these sentences, these fragments of text, and convert them to tokens. So let's do that. So this really what it does is it, for example, words such as visually stunning. So what Distilbert does is basically a byte pair type tokenization, where you break down the word, say, stunning into stun and ing, right? Or rumination as rumin and shun, right? So some tokens are words, some tokens are fragments of words. Okay, and each token will be assigned a number, a code. So let's see how they look like. So let's print the contents of tokenized. The zeroth review will be basically a sequence of sequence tokens. So the word A, for example, right, is basically the token index 1037. You can see 1037 in the third token of the first of review number 3. It's the third token. So you can see each, so words and word fragments have been encoded as token indices. Other things to note here. So there are 2000 such reviews, so therefore 2000 sequence of tokens. The first token is always 101. So what we did here is we added so-called special tokens. So what the tokenizer will do in this case will be to add like a token at the beginning of each review and the end. So the CLS, these have names. So these are called CLS and SEP. SEP marks the end of a sentence, whereas CL or a review, right? A CLS marks the start. Okay, so the end will be some other token index. Okay, let's keep going. Also, it's a list of list of encodings, right? Each encoding may have variable length because each review is variable length. Transformers require that you have the same length. So all inputs are the same length. Therefore, you need to do some padding. Let's pad all of them. Okay. So padded will have basically, so you're taking the longest sequence of tokens in, I don't know which one it is, but see what's max length. Let's examine some of this. So the longest such sequences of length 59. So everything has been padded to 59. Let's see. So padded is padded and padded.shape. So padded is the tokenized features, but zero padding to make sure that everything is the same length. And that, oops, sorry, shape. And you can see they're padded to size 59. Okay. and a bunch of zeros. Well, when we compute attention on such feature matrices, mainly to scaling issues. So there's also something called attention mask, which you can specify. And basically what this does is tell the attention mechanism to ignore all these zeros. That's all there is. Okay. Finally, we'll take these tokenized embeddings and then pass it through our Distilbert model. So this will give us feature embeddings for each review. This will take some time because again, this is a very large model. So I have to wait until all of the 2000 different tokenized embeddings for each review passes through the entire Distilbert model. Okay, so that took about 2 to 3 minutes. Okay, cool. So last hidden state is the output of the Distilbert model, and this will give you a bunch of different features. We don't need all of them. We need only part of the feature embedding that will extract using. So slice the beginning of each feature. That should be enough for this particular task. Could keep all of it if you like, but makes the classifier a bit harder. Anyway, so just take a part of the embedding, and that should be enough. Okay, so how big is this? Let's see. So this should be. So the feature embedding now should look like something like this. So this is again an array of size 2000 by 768. So before we started with tokens of size 59 for each review. Now we've been embedded each review into a feature space of size 768 and 2000 such features. Okay. So that's basically it. Let's also get the labels out. So now we have features. We have a bunch of labels. We can train a classifier. These features are already good enough. So this feature vector should capture semantic information of the entire review. It should be already good enough. So let's train a classifier for this kind of simple data set. Just a binary, a logistic classifier. Just binary classification is enough. We can just use the sklearn inbuilt function to do that. In fact, we'll also not do any parameter tweaking, just take it out of the box. Let's just fit a logistic regression model and see how it works. And we get 82%. So not too bad, right? So 50% is chance, 82% is good, I think. Let's see. I don't remember exactly. Remember correctly, picking the regularizer something like 5 should improve things. See if that does better. 81 doesn't. Okay. So we could just do a hyperparameter search to improve things. But anyway, we're already getting 83% here. For the record, 95% is like the best possible you can get on this data set. So as you can see, simple logistic regression is already getting this much accuracy. Yeah. So there you go. So this is a simple demo of how this a model such as Distilbert or other BERT type models can be used to extract meaningful feature embeddings to perform tasks such as classification or other kinds of text processing problems.